When working with three-dimensional data, choice of representation is both critical and non-obvious, as unlike natural images, 3D data can come in a variety of formats which are not necessarily arranged in a regular grid. We present evidence for the viability of voxelated representations for use in discriminative computer vision tasks. Building off our previous work with voxel-based variational autoencoders, we present a deep, voxel-based convolutional neural network for 3D object classification. Our architecture is based on the inception and pre-activation ResNet architectures with stochastic depth, and improves the state-of-the-art on both subsets of the ModelNet dataset by a relative 50%, while using significantly fewer parameters and less model views than the next leading method. A link to a GitHub repo with both the VAE and classifier code is available below, along with a link to the paper describing both generative and discriminative models. We initially experimented with very simple Voxception blocks, concatenating 1x1x1 filters with 3x3x3 filters for non-downsampling layers. For downsampling layers, we stack 3x3x3 convolutions with strided pooling operations, using both max and average pooling, and concatenate those features with strided 3x3x3 and 1x1x1 convolutions. Our intent is for the downsampling layers to let the network learn the best relative weighting of the various downsampling methods, maximizing propagation of information while still producing a more compact representation. Our Voxception architecture consists of 4 Voxception blocks and 3 Voxception downsample blocks, and obtains 90.5% single model accuracy when averaging predictions across 12 rotated instances. We then moved to truly deep networks by designing Voxception ResNet blocks. These blocks are also fairly simple and are just a concatenation of the 2 ResNet blocks proposed in the original ResNet paper. We stack 3 of these blocks together with a Voxception downsample block to produce a single computational unit, then stack 4 of these units, along with some standard convolutions, global pooling, and fully connected layers at the output to produce a 45-layer network. All of our blocks use pre-activation, meaning nonlinearities are applied after the residual sum, and stochastic network depth, meaning the nonlinear path of each residual block is randomly dropped with a set probability. Aside from the final softmax layer, we use the exponential linear unit activation function and batch normalization throughout the network. Our best single model, trained on 24 rotated views of each instance and tested by averaging predictions across 12 rotated instances, achieves 91.33% accuracy on ModelNet 40 and 93.6% accuracy when trained and tested on ModelNet 10. An ensemble of 5 Voxception ResNet models and 1 Voxception model achieved 95.54% accuracy on ModelNet 40 and 97.14% accuracy on ModelNet 10 when trained on ModelNet 40. We report this accuracy for consistency with prior results, but also note that an identical ensemble trained and tested on ModelNet 10 achieves 94.71% accuracy. This is perhaps unsurprising, but still interesting from a transfer learning perspective. Even though we did not show the model any additional instances from the ModelNet 10 subset, by learning to discriminate between a larger number of classes, the model better learns to discriminate between a subset of those classes. We also note that some of our larger ensembles, especially those that mix predictions averaged across both 12 and 24 rotations, yield even higher performance, but we suspect these results to not be general and do not claim them. The 3 most recent systems to achieve state-of-the-art on ModelNet 40 have all used 2D Convnets, pre-trained on ImageNet, then fine-tuned and tested on multiple 2D renderings of the 3D CAD models. The previous state-of-the-art, FusionNets, made additional use of Convnets that operated on voxelated model representations, but only achieved a 0.1% improvement over the next best multi-view Convnet system. All previous systems which implemented Convnets for voxelated representations have done so with relatively shallow networks with 5 or fewer layers. VoxNet originally applied volumetric convolutions to object recognition, and orientation-boosted voxelnets, which, despite their name, are not an ensemble method, improved upon VoxNet by augmenting the classification task with an orientation estimation task, though they only report results for the ModelNet 10 subset. Interestingly, FusionNets do not use volumetric convolutions, but instead treat the third spatial dimension as analogous to an RGB channel in a 2D image, meaning that from a volumetric convolution point of view, their voxel-based Convnets have one filter per layer, with that filter having one dimension equal to the entire spatial extent of the previous layer. Both our single models and our ensembles are trained from scratch and outperform all previous methods, and despite their substantially increased depth, our networks have 1/6 as many parameters as the previous state-of-the-art Fusion nets, and only require at most 24 rotated instances, compared to Fusion Net's 60. Our best single model also attains 89% accuracy on ModelNet 40 when tested using only a single view, suggesting that averaging across rotations may not in the future be necessary. Finally, we believe that there is still plenty of low-hanging fruit ripe for the taking, with just a little bit of work. Some simple things we would suggest trying include refining the voxel grid beyond 32 by 32 by 32 to increase spatial resolution and improve the available detail, changing the voxel grid to be real valued rather than binary valued based on the percentage of space occupied by the instance at each grid element. This could perhaps also be used with the variational autoencoder. Experimenting more with data augmentation, such as rotating about random axes or just adding more rotations about the gravity axis, random crops or random rescaling, and trying out different Voxception architectures, downsampling methods, and activation functions. Our code was originally adopted from the VoxNet source code and is implemented in Theano with lasagna wrappers.